Okay, I'm starting recording, and from now onwards, I will answer questions only related to the lecture, because otherwise it will distract people. So, yeah, binary search, you're able to see now, right? My screen with the lecture. Okay, cool. I will share week 2 that you can see. All the tasks which is here, only one we won't cover in the class. Find peak, we won't cover, but the rest we will cover today. So what is the trick here? I will just make some slight introduction that you understand. Topic is quite tough. If we were discussing during the 2-pointer, we can strictly divide it to the patterns, and we can identify, okay, during the interview, we can see what kind of 2-pointers we can use here. Well, for binary search, when you see LeetCode task or a task interview, it could be solved by different patterns, templates, which is used during the binary search. Today, I will start this lecture from the definitions, and then we will solve for a task, which is cover the most popular interview questions. But again, all this, I will provide the most, which is I found the most simple and understandable solution. I hope you will find them as well. But meanwhile, all this binary search could be solved slightly different from what I will explain today. Okay, let's get started. So, what is the binary search? Binary search, if you will look at this array, we have the whole array. So binary search, in nutshell, is when we can divide our array, and we can scope our search to one of the part. And then we can divide it again we scope to the another part. Yeah, here, binary search is an algorithm for search for value in a sorted data set. Yes, this is the prerequisite of the binary search. It should be sorted data. Later on, we will cover some examples, like find peak and sorted in rotated search, which is not really sorted data, but still it is predictable data. And we also can use binary search as well. No, it's not like merge sort. It is, you also divide, but then you merge. It is different things, but it is similar. So even experienced developer can find it's quite tricky. Why? Because we should, how should boundaries variable like left and right? Should we use left less than right, or left equal or less than right for exit condition? How should the boundaries variable be updated? Like when we're taking decision how to narrow search, we're using like left mid, or it should be left mid plus 1, which just means we excluding midpoint, or we including the midpoint. This kind of things make all binary search problem is quite tricky, very tricky, I would say. So there is steps which is includes for binary search. First, it's we will cover all of them in depth. Here, I will explain all of them. So first, you need to define the search space. Then you need to define the behavior inside the loop for narrowing the search space. Choose an existing condition for while loop and return the correct value. So now I'm moving to type div. Let's discuss what is means to define the search space. The search space encompasses all possible values that may include the value we are searching for. For instance, when we're searching for a target in a sorted array, the search space should cover the array, as a target could be anywhere within it. So this is our search space. I will use these terminologies during the solving task. Now, narrowing the search space. What does it mean? Narrowing the search space involves progressively moving the left and right pointers inwards until the search space is reduced to one element or none. Because the target of binary search to find either one or it could not be present. So at each point in binary search, we need to decide how to narrow the search space. So we can either narrow it towards left, like in these examples, we move right, means we narrow search to the left, or the opposite, we narrow towards to the right. For this, in order to narrow search space, we're using midpoint. Here's the midpoint. We decided whether to move left or right pointer based on the value in the middle of the search space. So we found mid, and then we decide whether we're moving left or right. Here's the general idea. If the value we are looking for it's to the right, narrow the search space towards right. Otherwise, narrow the search space towards the left. So, for example, if we will have here array which is started from 1 and 7, and we're looking in the mid, for example, it's our 4, and our target will be here. Target, we're looking for 5. Then when we see midpoint is equal 4, then we're deciding, okay, we compare to the target, and we see that on the left side there can't be 5 because the array is sorted. Then we need to narrow our search space towards right to this part, because our target most likely present in this part. Yeah. To narrow the search space towards the right, there are two options. We can, so it's applicable to the right as well. I just take left as an example, but there could be like right equal mid plus 1 or right equal the mid. The difference is when we're, so we do this if the midpoint value is definitely not the value we are looking for and should be excluded from the search space. So for example, here, we know that our mid is definitely not 5. Then there is no sense to include mid in our search. Then we will see like left mid plus 1. We're excluding this midpoint. 4 is not in our search anymore. But if, for example, we have duplicates, and we will look at the some examples where we have found first and last occurrence of the elements in the sorted array, this could be duplicates. Then if our midpoint is actually equals to our target, we should still keep it. And then we are not excluding. Then we will do left equals mid. So this is within the practice only. There is no like white or black when you can use this one or not this one. So this will comes with practice. We will solve 4 tasks today, and we will discuss all the steps, how we take a decision. And then you will do homeworks, and I encourage you to solve more. That's how this thinking comes during the practice. So, trick to remember, if you're trying to include mid, use right mid. If you're trying to exclude mid, use right mid minus 1 or left mid plus 1. At this point, do you have any questions? You are not assume. It's usually in the description will be. If this array has duplicates, then you include it. If there is no duplicates, then array definitely not. So you should look at the constraint and description of the task. So I'm moving then how we are calculating the midpoint. In most cases, the midpoint is calculated using this formula. It is in Python. We're using this formula. But in different languages like Java and C++, we can't use this formula because there is risk that we will hit integer overflow. That's why when you're solving a task in Java or C++, you calculate your mid usually this way. This divide by 2. Is this understandable? Why we're using this formula? Why it is suggested to use this formula instead of this? Or I can dive deep a little bit, and there is some descriptions. So I'm moving. If this thumbs means I'm moving, right? Okay, cool.
Sorry, Lilia, I didn't understand why we do left plus the second formula. I know you said integer overflow, but how does it work in the sense? Can you explain a little bit about integer overflow?
Sure. Okay, so if left plus right is greater than the maximum int value, we have this maximum int value, right, which is 2 in degree 31. And once this value is above, in Java, it will be overflow to negative value. So once int will be breaching the allowed range of the value, which we can hold in the int. So it will in Java and C++, it will automatically overflow to negative value, and then we will ending up. 1 second, it's. Then we will end it up with array index out of bound. At this point, it is understandable. So, yeah.
Sorry, I didn't understand what that 31 minus 1 was.
It is something which is type int. If you will Google, for example, type int Java allowed range. See, there is each type has their range. Once we will breach this range, it will automatically will be another value.
Right.
This is the point. This is the point to how we avoiding this in the binary search. Instead of doing left plus right, because it will automatically be a huge number. Could be a huge number, depends on the constraints and on the input. Then we're doing then we are hacking. So basically, like if we take as an example, 2 trees, one is 200, another 210. So what we're doing because we need just to find the diff, and then we are just plus to the left. It will be the same result like left plus right divided by 2. I'm not from the C++ background, Nika, so I'm not sure. You can, I believe you can use long or something like in Java. So now it is clear. Okay. Moving on. So choosing an exit condition in binary search. So there is usually 2 conditions. It's while left less than right, or while left less or equal right. What is the difference between them? When the exit condition left less than right, the while loop will break when left and right meet. Here. On the other hand, when left less or equal right and once, then left is suppress right. As you can see, right jump towards to left. So we just suppressed. It depends. So usually when you're looking for exact number in the binary search, and in classic templates of the binary search, and you know that there is could be target, or there is could be target, and you're looking for particular exact number, then probably you will use this one. But when you're looking for condition, like you need to find like insertion point. Even with insertion point, you can use both. But for example, you need to find, like we will cover what is the lower bound and the upper bound. When you're looking for condition and not for exact target, then you should use left-right. And it's more common. Like 80% of the binary search is actually implemented with this condition, with this exit condition, because most of the binary search is focused on finding rather conditions than value itself. We will start practicing, and we will discuss it, and hopefully it will click. It's also quite a tricky one. So returning the correct value. As I previously mentioned, the while loop terminates once we narrow down the search space down to final value, assuming no value was returned during early iteration. It could be that in your while loop, you have condition where you're actually equals to target. Then you can return right from the loop. But sometimes we are doing a while loop where we are not checking if it's target or not. Then you need to return the correct value after looping. And pointed it by both left or right. So basically, usually what we're doing in binary search, we return the left index. Yes, so and time complexity. Because most of the tasks which we can solve with binary search can be solved with linear search at first, because it's a sorted array. And during interview, when you have sorted array, usually it's interviewer is expecting from you that you will solve it with binary search rather than with linear search. But all the tasks which is you can solve with binary search, you can solve with linear search. Kind of, yes. It is. There is 2 pointers. You're also taking decision how to move them based on the middle. Yes.
Sorry, I don't understand how this is different from linear search, because you are not, you're still moving linearly, isn't it?
No, you're not moving linearly. Let me one more time to explain. You're taking this, your initial input array. What you're doing from the beginning, you find the midpoint. And assume your 9 is your midpoint. You are checking your left against 9, and you're checking your right against 9. And you're taking decision which part of array take, either right one or either left one. And means that you're all the time on each iteration, you're narrowing your search by dividing your array on 2 halves. And it's give us time complexity log n. It's no longer linear one.
Right. Okay. Like this is like a dictionary search, isn't it?
Yes, exactly. Yeah. Yeah.
Okay.
So, and yeah, because if it will be what is the linear one, you just going through the whole array and you're trying to find your number, your target. It could be present, it could not be present. So worst case will be in linear search or 10.
Yeah. So you're saying that before we go even linear here, we are figuring out which space in the array is our target in, isn't it?
We are not doing linear search at all here. Eventually, you will find just one element. You will divide until you will end it up with just one element, and then you will return this one.
Right. Okay.
So
When we reach the end of this search, let's say we were looking for 21 in this case, which pointer would be pointing at 21? Would it be mid or left or right?
usually it is left. But
Okay.
it is also depend. Sometimes it's left -1, sometimes it's left +1. It depends how you implemented it. There is no ultimate like what you should return. We will try to solve 4 of them. We will try to train this thinking process, how we defining what we need to return, how we defining the exit condition, how we defining the space, how we should think, how we should narrow down to the left or to the right, and how we should calculate the midpoint. But ultimately, all these tasks could be solved very differently, not very differently, but with some customizations.
Okay, thank you.
Yeah. So yeah, this is terminologies. Now let's move to the task, because I think it's the best way to practice. So first will be a problem, find the insertion index. This one, I will, 1 second, so this task could be solved with the classic pattern, where I will just make the introduction. So you can solve this one, which I'm not going to cover in this section. This is our classic one pattern, where you're doing your meet based on our formula, and then you're saying like nums meet will be target, then you are returning target, and then if it's not, then you're checking if nums meet less or equals like left, for example. I think there should be less. Then we are saying that our left will be mid +1, and the other way it will be our right, which will be mid -1. This is the template for the classic one. But this task, so in this task could be solved with this template, with the classic one. But in this one example, I want to cover how we are searching for lower bound condition in the binary search, because it's more popular questions. That Okay. Okay. So to understand what is the lower bound and upper bound, I will jump a little bit to another task. So just to give you an idea, in this task, we will look for lower bound and upper bound condition. So we have duplicate, and we need to find the first accuracy index of this duplicate and the last accuracy index. That's what we are calling lower bound. Means when we identify that there is something which is equal our target, but we know there is some duplicates. It doesn't matter if duplicates is all the same numbers, or it's just condition which is satisfy us. So basically, there is in first task, which is we will cover, will be condition which is will be satisfy us, but we need to find in insertion point the lower bound, the first condition which is satisfy actually us, and this will be the leftmost. And if we're looking for upper bound, it means there is we have conditions on the left side which is all satisfy us, but we need to find the rightmost elements which will satisfy this condition. This is in a nutshell what is the lower bound and upper bound. And most of the search search binary task is focusing on the find lower bound condition or upper bound conditions. So, any questions now?
I have a question, sorry. So you said that mid will never be the target, correct? But let's say there are so many duplicates in the array that when you calculate the mid by that formula we looked in the last slide, you end up with mid being the target. So how do you know whether the space should be narrowed on the left or the right side?
We will learn in this task.
Okay, thank you.
So, okay, now let's focus on the description. You are given a sorted array that contains unique values, in this case, along with an integer target. If array contains the target value, return its index. Otherwise, return the insertion index, the index where the target would be inserted to maintain the sorted order. So from the description you see, you're given sorted array. Array is contain unique values. So description now understandable. What is asked from us? What we need to find? Yes, if it's not sorted, probably in order to solve it with binary search, you need to sort it. But there could be different patterns, so you should understand from the task description whether you can apply to binary search. Then yes, it makes sense to sort it. Okay, cool. Moving then.
If we sort it, I just have a question. If we sort it, then you change the index of the target, isn't it? Then why would you sort it in that case?
No, there was question if it's not sorted. Sometimes you can apply binary search to some task. But from the initial description, you know that you don't have array which is sorted one.
Yeah.
But you could solve this task with binary search. It's not about finding index. It could be different one.
Okay.
But you're just thinking, there was questions, just question on the chat, should we sort to solve for binary search? In question is, yes, if you're going with binary search, your array should be sorted.
Okay, makes sense. Thank you.
So the intuitions, we for sure can apply linear search right here. It's pretty easy. Just go over the in for loop, just check every elements and find the position, whether it is present or it's not present. So by maintaining the sorted order, yeah, I will explain. So it means in this case, we have this target, which is present in the array. In this case, we don't have target 6, and we need to find where we want to insert this 6. And it should be here, right, to maintain the sorted order. So we can't insert 6 after 9, or we can't insert 6 after 1 or 2. That's what mean the okay, cool. Intuition. If the target is in a sorted array, return an index. If it's not return the index, where it should be insert to keep the array sorted. So we have two cases in this task. First case, target exists in the array and target 4. We will find and we will return. Case 2, the target doesn't exist in the array. So if the target isn't in the array, its insertion, the lower bound is the first index where the value is greater. Just 1 second, it should be somewhere here. If the target isn't in the array, its insertion index is the position of the first number greater than the target. For example, in the second diagram, the target is 6, and the first number greater than 6 is 7. So the insertion index is right before 7. Does it make sense? Yeah. Connie, you want to ask or it? Okay.
Sorry, I was meant to do a thumbs up and then press the wrong button.
Okay, it's fine. So this should be clear. So the target isn't in the array. It is insertion index is the position of the first number greater than the target, like we see in this case. And it is lower bound, actually. Is the first index where the value is greater than or equal to target. That's the terminologies. And it is the terminologies of lower bound. Since we don't know if the target exists in the sorted array, we handle both cases by finding the first value that is greater than or equal to the target. That's how we handle both conditions. In this approach, whether the target is present or not. So in this case, we're working with condition. We are not working with value. This is our condition, which is we need to meet during our binary search. And we call it lower bound. Again, finding the lower bound is equivalent to finding the leftmost value. Let's try to solve it. First, define the search space. We will take example, this one, where its target actually is present. And then we will move to the another case where target is not present. Okay. So our search space will be the whole array, right? And it could be that actually our target, for example, instead of 4, if here will be 10, then so it is out of the array, right? It will be somewhere here. Then our space is not limited to n minus 1, but we will take it from 0 to n, our search, in this case of task. Does it make sense? So again, you're thinking, you take the description and you start to think, what should be my space, my search space? Whether it should be limited to the n minus 1 or it should include actually n.
Sorry, I didn't understand this because let's say your target is now 15, right? What
Yes.
is the point of extending to n because you can't insert?
You can. After 9, you will insert your 15. This will be 7 will be the place for your 9.
Oh, okay.
Because you need to insert value. It doesn't make here. See, there is 3 is missing, but it is still sorted. It doesn't make sense that you have 1, 2, 3, 4, 5, 7, 8, 9. There is could be value which is missing. You just find, for example, if there is 15 instead, you just find what should be the index for this array. And you know that all these elements you have, and you have 9, which is ending this array, means 15 should go after 9.
Right.
Sorry, I have one query, Laila. So you have mentioned that here we will be implementing a logic where we will be checking target with values, right? For example, like
Yes.
if it is, if value is greater than equal to target, why are we checking that and not value less than equal to target? Because for insertion, like in that example of 10 or 15, so we won't be having any element, right? So we have to compare it with the last element.
Why we are not checking value less than target?
Yeah, why we are not taking other way around, like value less than equal to target? Like in this case, for example, we were comparing, like for 6, we were comparing with 7 and not with the 5.
Yes, let me try to explain it. So, for example, your target is 6, right? And you're asking whether the value could be less than target. So, can you come again?
Yeah, so value less than equal to target.
Mhm.
So in this case, why we are not comparing 6 with 5?
6 with 5. Yes. So 6 with 5. Let me think. Then I believe it could be potentially solved. This will be a upper bound you're looking in this case. It could be potentially solved, I believe. So for example, if we take 5 here and we will compare it with
Target, whether 6 is
yeah,
greater than
yeah.
5.
I'm
Which
trying to it could I'm trying to just to think whether it is possible or not possible, because this will be so let me just think 1 second. So we have 5, which is less than target. We find the value. We have value, so this is will be 6, and then we are saying 5.
Maybe I think it's because in this condition it might work good, but let's say we have a target of 15 and we look for 15 less than sorry 9 less than 15. So in that case it might fail, I believe. So that's the reason the other way around might work. The other condition might work.
Yeah, I believe the in the middle as well. I just trying to think how to prove that it's not going to work as well. So the idea with lower bound that, for example, here we see that 6 should be here, and we know all this condition will meet our target, but we need to find the lowest one, which is will be 7, because we can potentially insert here 6. We can potentially insert here 6. So we found the condition of this subarray, but we need to find the lower bound. Let's think. Now, if we found the condition, so for example, we have 1, 2, 4, 5 here, and we found that 5 is the other way, like you asked. And here we see this potentially is meet our condition. Then we need to go down and to check whether this one is also fit to us.
Mhm.
Probably you will find out that 4 and no, you will keep going left, right?
Yeah, got it.
Keep going, so it won't work in this
Yeah.
case.
It will
Yes.
compare all the element, but
Yes.
in this it won't, because we know that 7 is the lowest one and our target is less than that. So no need to
Yes.
compare with 8 and 9.
Yes.
Got it.
So does it make sense for folks on the phone? By the way, very great question.
Okay.
Okay.
I have one question. When you say lower bound, is that lower bound because sometimes we say left, right, and then we say lower
Yeah,
bound?
left. When I'm saying left, it's mean lower bound. It's
Okay.
leftmost, and
Okay.
upper bound it's rightmost.
Okay. Thank you.
Yeah. So if we have a target which is exist actually in the array, so we're defining the space. It will be our left. It is indexes, folks, here 0, 7, and our mid index is 3. What we're doing, we're taking mid and we're asking whether it's more than our target, and it is. So in this case, if it is, then so what is this? It will be 5. In this case, our nums mid, which is 5, it's more than 4. Yes. Then we're initially the midpoint is positioned as the element 5, which is the number that satisfies the condition of the being greater than or equal to the target, because we are targeting for 4 and 5 is actually satisfy our condition. This means that the lower bound is either at the midpoint, it's actually could be our midpoint, or it could be something on the left, right? This is makes sense now. So it could, 1 second. This is our midpoint. This is our element. it is satisfy our condition, and now we should decide whether to move left or to the right. And if it's satisfy, it could be still our answer. We don't know if there is other elements. So, but we know that on the right, there is all these values will be satisfy our condition. There is no sense to look for them because we are actually focusing on the lower bound in this case. Then we're saying that, okay, right will be meet. Why meet and not meet -1? Because the condition actually is satisfied, and we are at this point, we are not sure if it's our answer. That's why we should keep it. And we're narrow our search to the left. And we will end it up with this array, which is which is half of the initial one. Does it make sense? Okay, thank you, folks. Now the midpoint is positioned at the element 2. The lower bound should be value greater than or equal to the target, which means the current midpoint is too small. So 2 is very small, so we make calculation. We found our mid. The calculation was done with the new right, which is 5 now, and which is left 1. And we calculate the new midpoint, which is 2. And now we are compare our 2 with our target. And we found out that 2 is actually small than 4. What we need to do, there is no sense us for checking the rest in this part. We need to move towards right. And we don't need to include this midpoint because 2 we know already is less than 4. And that's why we are taking left mid +1 at this point. And we narrow search to the 2 elements, 4 and 5 at this point. Now again, we're doing the same. We're taking our left, which is currently 4, our 5, which is currently 5.
Sorry, one quick question. You know where we compared nums of mid is less than 4? Why we not compare? Why is it not nums of mid less than equal to 4? Because it is also possible, right?
Say again?
So you know where we said value is less than target. In this case, when we move the left pointer, before we move the left pointer, we are comparing whether value is less than target. Why is it not values less than equal to target?
No. This is we're still having the same check. I just wrote it here to say why we are taking this decision in this case. But we all the time just having only one condition against which we're checking. I will let me see if I have code here actually. No, I don't have. I didn't include code. So basically, in the while loop, we still have only one condition. Let me see if I have somewhere this.
See, I mean to say here where, for example, sorry, can you scroll up where you circle further up a little bit?
Yeah, you are asking me about this, right?
I'm asking you about this, but I'm also comparing the previous check. Before we move the right pointer, we check whether value is greater than or equal to the target, right?
Yes.
Here,
yes.
Right? But when we check the left pointer, when we want to move the left pointer, we are only checking less than, but not including.
No. This I just explaining why we're taking decision to the left. You will always have only one condition where your value is actually more and all equals the target. This is the only one piece of code which is you will compare and take decision whether you need. This is I just explaining you why we decided move left to the mid. But in code you will have just one condition.
Okay. And if that's the real condition that we will write in the code, then what is the point of moving left to mid +1 without knowing whether it is less than or equal to? Because it could also be left equal to mid, isn't it?
No, you know that your 2 is not equal to 4, right? when you're comparing, you have your meet right here. You take this number and you compare against the target here, and you know that you 2 is not 4.
Okay. Yeah. Oh, yeah. Understood. Yeah. Thank you.
Yeah, that's why I just wrote this one, why we take this solution, why we have this decision, because we know exactly that 2 is not 4. And there is no sense for us to keep this meet plus 1. Why we are here saying, because here we take 5. And in this particular task, there is could be present target, which is 4, and could not be present target, right?
Yeah.
If the target is not present, then we need to find insertion point. So for example, you still don't know if in this array is 4 is actually present, but 5 potentially could satisfy our condition, because we need to find insertion point. And if there is 4 is not present in this array, we will say that 4 should be insert before 5.
Makes sense. Yeah.
That's why we're keeping in the loop meet, and it
Okay.
will override. But in this case, we know that 2 is not 4, then we're moving, because we are looking for lower bound.
Yeah.
Everything what is on the left side, on the right side, is all will satisfy our condition. But everything what is on the left side, it doesn't satisfy our condition from here. That's why we are just cut this part of array.
Okay.
No. So and we're ending up with 2 elements here. We keep doing the same iteration, like left 4, mid 4, and right 5 after our calculation. We know that again our mid is more or equal than 4. Then we're taking a decision to move right pointer, because again we satisfy our condition here. We know that it will satisfy us, so we don't really need anymore this 5, because we found the best option for satisfying our condition. That's why we are saying, okay, right will be our mean, and eventually we will exit the loop, because now left point to the 4 and right point to the 4, and we will return our answer as a left. This is the case where the actually target is the present in the array. Does it make sense?
Can you just once again just repeat the last 2 steps? Sorry.
Yeah, sure. So once we narrow our array to the 2 elements now, right?
Yeah.
Because we were taking decision which half we want to iterate. And eventually we have array which is contain just 4 and 5. The rest are already not interesting, because we just cut all this part. It's not some is satisfy right is all satisfy our condition, but we know there is best option for us, and left it doesn't satisfy our condition. So at this point, left will be 4, mid 4, and right. We make a calculation on the we checking nums mid 4. Then we take decision that right now our mid. And before we have this while loop in our code, which is while will be left and right. And as we based on different conditions here, we are moving, we're deciding left will be mid plus 1 if, so for example, or else here will be our right, which is we decided that we are keeping, because right is satisfying us. So eventually we will walk through the whole array, and we will end up with just one value, which is and we hit this condition, our exiting condition, where left start point to the right, and this will be our answer.
Yeah. Thank you.
Okay. Let's let's quickly walk through the case where target doesn't exist in the array. So we have the initial one. We're taking the same search. We're also evaluating the conditions, where to move left or right. Eventually we will ended up with 7, because currently we are looking for target where we need to insert target 6. As we can see, by the end of binary search, we narrow down the search space to signal value, identify index 4 as the insertion index. So we found the best condition which satisfies us, and we just return left. It will be point to 7. We are saying that we need to insert at the index 7, and the rest will be just moved elements in the array. So summary, just for clarity. The mid for both cases, I'm a little bit speeding up because we have 3 more, and it is not the toughest one. The midpoint value is greater than or equal to the target indicates the lower bound is either at the midpoint or it's left. In this case, we narrow search space toward the left, ensuring the midpoint is included, as we discussed, right? And if case 2, the midpoint value is less than the target, indicating the lower bound in somewhere to the right. In this case, we narrow the search space towards the right, ensuring the midpoint is excluded. This is what is this clear, folks? The summary. Okay, cool. Now moving on to the another one, which is also popular task, LeetCode question, where you need to find first and last accuracy of the number. Let's start from the description. Given an array of integers sorted in non-decreasing order, return the first and last indexes of the target number. If target is not found, return -1 and -1. So we have initial array, which is contain duplicates, and we have target our 4. In this case, we need to return our 3 index and 5. The first and last accuracy of number 4 are indexes 3 and 5 respectively. That is this clear description? Okay, cool. A brute force solution to this problem involves, as I mentioned, linear search before. So let's keep it. The challenge of using binary search in this case, that we need to find 2 separate accuracy of the same number. This means that standard binary search alone isn't sufficient. To help us to find solution, we will find lower bound as we did in previous task, and we will try to find upper bound in this case. To perform binary search means in this task, you actually need to perform twice binary search, but slightly implemented differently. One binary search will be implemented to find lower bound, and another one will be implemented to find upper bound. Not sure. Okay. I included code. So just maybe someone click better when he or she solves the code. So basically, we will run 2 binary search on the same array. Find lower bound and then upper bound. There is 2 different functions. They quite similar, but with some tweak, which we will now discuss. So that's how we are going to solve this problem. Let's again cover lower bound binary search. To find the start position of the target, let's first define the search space. The target could be anywhere in the array, so the search space should be encompass all the indexes. Again, we are defining the space search. It's the whole array. Here, it's not beyond, because here in the description, it's told us if there is no target in the array, we're returning -1, -1. So we are including only space, the length of our array means n -1. Okay. Next, let's figure it out how to narrow the search. At each point in the binary search, there are 3 conditions to consider based on the midpoint value. Currently, we are focusing on the function for lower bound search. Don't be confused. Then I will move to the upper. So when it's greater than target, when it's less than target, and when it is actually equal to the target. In each of these cases, think about where target in the relation to the to the midpoint. First, let's cover again. Midpoint value is greater than target, not greater or equals like we were looking in the previous one. Here we are looking for strictly greater than target. If the midpoint is greater than target, the target must be on the left. So we move the search to the left. Does it make sense? Okay, cool. So we're looking for 4. We found the midpoint and we're narrowing our search towards left in this case. Let's look at the second condition. Midpoint value is less than the target, also strictly less. Then what we need to do? For example, we found our midpoint, which is 3, and then we are narrowing our search towards right. So that's I put the example. So we have initial array. We define it left, right, mid. At the mid, we're taking decision. If it's strictly greater, then we're narrowing search towards left. If it's strictly less than target, we're narrowing search towards target. Eventually, we will ending up with, for example, with this array. Here, the third condition is appear. Midpoint value is actually equal to the target. Now is when things get interesting at this point. This is the lower bound of the target value. It could be, right? We don't know. So now we are working on this part of array. And we need to understand whether it's our lower bound or its lower bound is somewhere on the left. How we're working in this case? If we don't know which possibility is true at the moment, we should narrow the search space towards left to continue looking for lower bound while also including the midpoint itself. Means if we're meeting target, which is mid, actually equals our target, what we are doing, we are trying to narrow our search to the left, but still we're keeping right, which is equals to mid, similar to what we did in the previous task, right? And eventually, our answer will be again left pointer, and we will narrow down, and we will eventually end it up with 4, and we will, in our exit, we will exit with left. This code for lower bound. As we discussed, we have 3 conditions. Let's first we are narrowing our search 0 to length -1. Then we are defining our exit point, left less than right. Then we're saying mid. This is Python. That's why mid is calculated this way. And then we are checking first condition. If nums mid is actually more than target, then we narrow search to the left. If the nums mid is less than target, then we are narrowing our search towards right. And if we found the target, which is equals, if a mid is actually equals to the target, we're narrowing to the left, but we are keeping our mid option because it could be our answer. This is very similar to what we just implemented in the previous one. Does it make sense? Any questions? Okay. Let's now focus on finding upper bound binary search. This is very similar to what we did for our lower bound binary search. The search space is the same. We handle cases where the midpoint is greater or less than the target in the same way. Does it make sense why we are handling them in the same way? when midpoint is greater and when midpoint is strictly less. This is because we're still searching for the same value, and it makes sense to just think against the midpoint where we should go left or to the right, based on if the midpoint is actually less or greater than target. The key difference here comes when midpoint equal to the target. Let's focus on this. So we did our research, and eventually we finish with the array, which is contain our duplicates. Now, similar to lower bound search, there are two possibilities. Either this is upper bound or it's not. Again, we are not sure which is true. So let's narrow the search space towards the right. In this case, we are narrowing search towards right instead of towards to the left, because we are looking for upper bound in this case. And before we were doing right equals mid, but now we have this difference, which is we are replace right with left, and left now equals to mid. Does it make sense at this point? But the problem with this solution currently, because we will ending up with infinite loop in binary search. Have you folks ever ended up with binary search when you're stuck in the infinite loop? Me, quite frequently. Infinite loop, then that we are looping a lot the iteration and we can't exit because our condition is not changed. So particularly in this case, it won't be changed. And if you never ended up or never you debugging this condition, so I encourage you to try to implement with stacking in the infinite loop. And then debug, and so basically to stack here, you just need to find mid the same way like we did for lower bound. Yes, the array is sorted. I will explain why we are ending up in the infinite loop here. So if we use left mid in our logic, we risk getting stuck in infinite loop here, left. And because left and mid will keep pointing to the same spot and the search doesn't move forward. This didn't happen in lower bound binary search because we use left, because we never used left as a midpoint. Why it's happened? Because I will copy this one to this one. How we are calculating actually mid? In our previous task and in lower bound, we're calculating the same way. We're calculating it the way this one. And this is we call left bias calculation of midpoint. Why it's left bias? Because, so for example, you have left, which is 0, and you have right, which is 3. When you're doing this 3 plus 0, and you divide this on 2, you will ending up actually with 1.1, but it will be circle, and you will receive 1. It is calling calculating the mid left bias. For upper bound, we need to calculate its right bias because we're looking for upper bound. That's how we're calculating. The difference is that we're just adding +1. And in this case, if we will calculate it, it will be our 2. we actually will be biased to the right. And that's how we want ending up in the infinite loop. We will moving actually to the right. And eventually we will exit out of this array, and we will find our upper bound index. So that's it about the find last and accuracy. This is the code snip. So the difference is only how we're defining mid. This is left bias because we're looking for lower bound, and this is right bias because we're looking for upper bound. And instead of here, we are keep our left as a mid, and here we are keeping our right, because in the first case where we're lower bound, we are searching towards left, and when we are looking for upper bound, we are looking for the right. Does it make sense? It's very silent, folks. I hope you're still with me.
No, it's silent because trying to understand what you said and trying to understand by
Just
seeing
ask
the code also.
questions. It's very tricky. Yes, very tricky. I didn't know before that it's so tricky.
We'll probably have to revisit it once again ourselves.
Yeah, it makes sense. So, okay, let's move.
Just
Mhm.
sorry, if you can again just explain this, why we are like dividing while we are incrementing. I mean, I understand the logic, kind of, like we are increasing, but it's not working out, like how it is different, like why we are ending up in infinite loop.
Yes. See, as we so we can try like to calculate it, right? Here. So, for example, let's just have this one too. Let's try to calculate this one. There is like our left. Now let's try to calculate. Probably it should work if we will work on this. So we will do 2, 0, and it will be our 1 here, right?
Yes.
So our mid will be here. Means our left should be mid, and it will be 1. And now we need to calculate again our mid, right? Because now we are narrow our
Towards
search
right.
to
Moving towards right, yeah.
yes. Now it's 1 and 2.
Yeah.
Now let's calculate again our mid. So it will be 2 plus 1, and here we divide it, and our mid again will be 1, right?
Yeah. Okay.
And we will start
Change.
endless that it will be. So you can try just when you will solve this task, just replace this mid with this one, and just try to debug in the console or on the paper.
Right. Got it.
Because you will keeping the pointing left and mid, and that's why you want moved. This is quite tricky about binary search. So you just need to first learn it by heart, and then to apply. And then the most you will apply, the most you will debug, and ending up in the situation. So after this, it will probably click in your mind how you should define the search space, how you should define the exit space, exit condition, how you define the mid, where you should include midpoint, where you shouldn't include midpoint. And to find such kind of infinite loop or some problems, it's usually needs just to debug with dry run. to writing on the each row what exactly you are receiving in this point. What is your mid, what is your left, what is your right. That's how you can find kind of these bugs and can fix them in the code. So it's not something which is particularly applied to this task and you can solve only this way. No, you can solve particularly this task first and last accuracy with different way. But I find this way is the most understandable and more easier because you're splitting on different free conditions where it's greater, strictly greater, less greater, then you find equal target, and then you decide it whether it's lower bound you're looking, whether it's upper bound. So, but the same task can be solved differently.
Right, Lilia?
Mm-hmm.
Cool.
Cool. Let's move on. Not this one. I wanted to cover, but this one. Okay, we have time for 2, I believe. Okay, this is very tricky one, but it is very, I noticed that it's very popular during the interview now. People ask. And if you never face, you would never know that it is actually a task which is solved with the binary search. So let's try from the description. You are given an array representing the height of trees and integer k representing the total length of woods that needs to be cut. For this task, a wood cutting machine is set to a certain height h. The machine cuts off the top part of the old tree taller than h, while trees shorter than h remain untouched. Our goal is to set the highest possible settings of woodcutter h so that it cuts at least k meters of the wood. Assume the woodcutter cannot be set higher than the height of the tallest tree in the forest. Example. I know it's still not clear, right? From the description, folks, what needs to be found. So these are our trees. And we have 4 trees with height 2, 6, 3, and 8. We need to find, and we have target, which is 7 of wood. The highest possible height setting that yield at least k7 meters of wood is h3, which yield 8 meters of the wood. Any higher settings higher than this will yield less than 7 meters. So the idea is, let me, okay, I have it here. So this is our trees. This is 2. This is 6. This is 3. And this is 8. So the idea is this, for example, here we have our machine, which is has some settings, how to cut. We can put the h for the machine to cut at the 8. Then it will ultimately cut nothing because as from the description, we were told that while the tree shorter than h remains untouched. But we need to have this k, which will be equal 7. So we need to cut something in order to sum up them and receive this k and 7. Then we can try to cut at the high 7. Then we will receive our k equals 1. This also not satisfied to our condition, right? Let's try to choose our 3. 2 won't be cut in this, and this one 3 as well won't be cut.
Sorry to cut the,
Yeah.
but will not k is equal to 2 because it's cutting the last 8th as well.
Say again?
For the 6 h is equal to 6, will not k be 2 because it will cut 6 and 8 as well.
No, it won't. equal or so it won't be attached. We choose 7 here, and
Oh.
that's why we're having this one only, which we can touch.
Ah.
And here, for example, this will be free, right? And we have here h for 6. It will be our free, and here we will cut 5. Does it make sense? Because we choose free, we have one tree which is free, but it will remain untouched. And this how we can find our value, which will be 8, which will satisfy this one. We don't need to find exactly 7, but we need to find something which will satisfy our condition. It could be 10, it could be 11, but 8 is pretty good. So we cut the least number of the tree, and we satisfy the condition.
Sorry, Lilia, I'm getting lost here. What is the condition? I didn't follow.
I'm on the description yet. What the task is asked for us. We are given as an input trees, and we have target 7. We need to cut so many. We need to find the optimal solution for the tree for the setting of the wood cutting machine. In this case, setting is H. For which we're setting our wood cutting machine. So assume this our cutting machine. We're setting it that we want to cut everything what is above free. What is the above free? And we have these trees. And if we setting this, we will figure it out that this one will be cut and this will be cut. We will receive woods. We will calculate them, and we will receive our target. This is the description of the task. What needs to find the proper setting for this machine.
So find the. I'm still not understanding this. So we are given different heights of the trees, right? And
yes.
What does K stand for?
K, it's sum of the woods after cutting. So assume you have 5 trees. You start cutting them, and you need to sum up after all the height which is you cut. So for example, you have 3 which is 6, but you didn't cut it's under 0. You cut it in the middle. Means we have free value from this tree, and you need to cut as many trees to satisfy this 7, but not as many at least. So you should be diligent. You should know you can cut all of them, and all of them in sum will give you 19, which is will still satisfy a solution of the task. But you need to find the least number of the trees, which is the least number which will satisfy. Does it make sense?
Yeah. So can you just go down to that? So you're saying that if we cut at 7, the tree that is of height 6 will give us 3 meters of wood, and the one which is 8, the tree that is 8 meters height will give us it's going to give us 4. So it's only 3 plus 1, 4, isn't it? It's to satisfy our requirement.
If you're setting at 7, you can cut only 1, and just 1 you will receive. K will be in this case 1, right? It won't satisfy. Okay, then what we need to do? We need to decrease our H. So for example, we can go with 6 at this point. And it will again cut anything. Then we go with 5. It will touch our 6. No, it will cut actually the 8, but it will give us 2. Then your decrease again your H to which one? It could be 6, it could be 5, it could be 4, but none of them won't satisfy this solution. The first which will be satisfied this solution, it will be actually free, but all others like 2, 1, and 0 is also will be satisfy our solution. But we need to find least age, which should be setting to the machine in order to satisfy to this target.
Right. And one other question, do we have to decrement by only 1 meter down, or can we just decrement the next?
No, I just, it's only description.
Okay.
Now I explained the description. Folks, is it clear the description of the task, what's asked from us? Because they're very tricky all the time, particularly this one. Okay. Intuition. At first, it may seem odd that this problem appears in the binary search chapter. After all, the array isn't fully sorted, right? Like we have these trees, it's not all sorted. But these are the classic examples where binary search is applied, not to the array values directly, but the search space. We use structure in the array, like sorted subarray, to guide our decision making. So now I will explain how we will end up with the binary search on this. So as I explained it, the tallest tree has height of 8, so we can set the high value to h, to anything between h, the most amount. I will just amount cut h where all three. I'm just looking what is the important to mention here. Yes, as I mentioned, this one, the most, if we're setting our to 0, we will most woodcut will be equals to 19. If we're setting to 8, then least then we are not cutting anything. It won't satisfy us. The 0 will give us 19, which is too much. We can do better, right? Instead of cutting all the trees. This is the idea of this task. Okay, as we increase woodcutter higher setting from h to 0 to h8, the amount of wood collected decreases. Our goal is to find the maximum age that still give us at least k meter of the found. And now, we can build kind of this array, right? This is h, which is 0, and this h8. And we know that h0 will still satisfy us, h1 will still satisfy us, h2 will still satisfy us, h3 will still satisfy us, but starting from h4, there is no way that we will satisfy solution. That's how we will ending up with binary search. So this, we built our structure on which we can actually run our binary search. Is it clear now? Okay. For this reason, we need to introduce function, which is will calculate. So basically, you are providing h3, you're cutting, you're doing calculation, sum, and you're compare. If it meets our target, then you either return true or the false. And this goal, on this goal, we actually were looking for our upper bound solution. Is it clear why we're looking here for upper bound solution, not lower bound? Yeah, Sandeep, you can tell.
Yeah, because we are looking for optimized tree, so we are looking for a high bound here.
Yes. Yeah, cool. Thank you. So we are looking for upper bound on this one. As such, we should use our mid calculation is different one, which is will be a right bias instead of left bias in this case.
Sorry, Lilia, just one quick question. Before we started searching for upper bound, we did sort the array, isn't it?
No, it is, we start working not on the array. So this one, our initial array of the trees. We have just 4 trees here. We have 2, 6, 3, and 8. It's just height. We started thinking about the task that we need to satisfy this target. In order to satisfy this target, we can cut all our trees, starting with h, which will be 0. Then we will cut all the trees, or we can cut nothing, and then we won't satisfy our solution. On this thinking process, we are building the array.
Oh,
This-
okay. So this is not the input array.
No, it is high. We figured out that our least satisfying solution is H0, or it could be H8. And now we are trying to figure it out what the solution should be satisfy our target. And with calculation, we will figure it out that H3 is the one optimal one, where we're cutting less trees, but it still satisfies us. All the rest is not. That's how you're ending up with the binary binary search solution for this task. Is it clear, Mina?
Yeah, it is clear. One quick question. So before we look at finding which is the upper bound, we have to generate this array, isn't it?
No, you should not to generate this array. For this purpose, you just introduce a function.
Oh,
Let me
okay.
see if I have, I have code here. So that's how code will looks like. You introduce this function, which is good enough enough boots, and it will return you boolean, which is true or false.
Right.
You will give and you will ask. If it's satisfying, then we are taking decision where left is our mid, or we are moving, which pointer we are moving towards. You don't need to generate anything. You're just introducing the function, which is taking as an input your mid potential target, potentially. So, for example, we forgot about true, false. It's black box for us. We're taking our high, which is 0 and 8. It's the maximum which is present. We're trying to find mid solution here. It's, for example, H3 or H4. We are giving input to this function here, and we ask, if I will, for example, cut at the level of 4, will I satisfy my solution? And at this point, you will receive true or false. If it's satisfying, then I will try the list. Then I will move to the left. Probably there is something which is even more satisfying.
Yeah. So in this case, K was. Can you just show what the K value was when the initial problem?
K,
Yeah. So K was 7, right?
yes.
So
You don't need to find exact 7. Everything what is well satisfied could be 7, 8, 9, 19, everything.
Right.
But something which is satisfying here.
Yeah. What I'm asking is, you took H0 to H8. Why is that? Do you just say K plus 1 is the maximum when I start?
Yes, the tallest tree has a height of 8, so we can set the high value H to anything between 0 to 8. The most amount of wood is cut at the H0. We know this, where all trees are cut from the bottom. The least amount of wood is cut at the H8, where no wood is cut at all. So because you need to find H, which will satisfy the condition. So basically, you will take the longest one and the shorter one, and you find between them the best solution, which will satisfy us. On the other hand, you already know that H0 will 100% satisfy us. You still don't know about 8. I mean, you know about 8. It won't satisfy us because it won't cut any tree at this point. So that's the search space which is you defined, and now you're trying to find the optimal solution, which is will try to will actually satisfy us.
Okay, makes sense.
It's a very tricky question. We can keep discussing this on Slack. I will post it. quite a few examples on this, and we can together to discuss, because I'm also quite still is not very comfortable with all these binary search things. Okay. Where we was upper bound. As such, we should use upper bound search. Let's first define the search space. Our search space should encompass all values of h between 0 and the high of the tallest tree in the array, as these are all possible answers. To figure it out how to narrow the search space, let's use the example below, setting left and right pointers to the end of the search space. So this is our initial array. We have left on the 0, right on the edge, and we figured out our midpoint. Initially, the midpoint is set to h4 at this at the first iteration. When we call cut enough wood, it returns false. It won't satisfy us. This means the highest setting is not yielding enough wood and is hence set too high. To find the lower highest setting, we should narrow our search space toward left. Is it clear? Okay. The next point is set to h2 at this iteration. When we call cut, it's returned true. This means the upper bound is either at the midpoint or it is right, as the upper bound is the rightmost high setting that cuts enough wood. So we have true. We're narrowing our search towards right, means we found our solution. That's why our left will still keep mid, because it could be our potential solution. So we're narrowing search space here to h2 inclusive, and we have h3 still to consider. It will be left and right. Next point is set to h3. When we call cut enough, it's returned true. So narrow the search space towards the right, because we found another one, even better solution than h2. Our left will be mid. Once the left and right pointers meet, we have located the upper bound high setting that cuts at least key meters of the wood. And there is some small summary and code snip. Any questions before I will move to our last one?
Sorry, could you scroll up a bit just so I can see the summary again?
Summary. Yes.
The summary and the, yeah, thank you.
So how would we know in an interview that, how do you spot that this is a binary search problem?
It's from practice. It's from practice. I will share more on this topic on the Slack. I will share the similar one, how during the interview you can spot actually that this is on the binary search.
Yeah, like last time you gave some indicators of,
Yes.
what 2-point approach will be. If you can give some indicators, that would be great.
Yes. I will do this. No.
Okay. Also, sorry, one quick question. Could this be even solved as a brute force approach? Let's say I'm seeing this problem first time. Can I initially start looking at this as a linear?
Yeah, I think so. Yeah. Need to think how to solve it with brute force solution. I mean, of course, you can try all the trees, all the highs, and calculate and eventually find the best solution. Yeah, 100% with the kind of linear search.
Okay. I actually have one last question. When we solve these problems in the HackerRank, they give something called constraints. I look at constraints, but I don't know how I should take that into account when I figure out the solution. Maybe after your last problem, can you just explain how constraints should be included as part of the solution?
I will cover it separately on the Slack, if you don't mind. because
Okay.
we left 15 minutes and there is another task which is I want to cover, but I will definitely cover these constraints. It's also a great question. It will require it like a good explanation. Okay, another one. This is slightly different from what we saw so far. Forgot about left bias and right bias, lower bound and upper bound. It's absolutely different one, binary search example. Find the target in rotated sorted array. So a rotated sorted array is an array of numbers sorted in ascending order, in which a portion of the array is moved from the beginning to the end. For example, a possible rotation, we have this one, which is sorted one, but it is a rotated sorted. Here, as you see, 1, 2 on the right, but 3, 4, 5 on the left. This is a still sorted array, but it is rotated one. Given a rotated sorted array of unique numbers, return the index of target value. If the target value is not present, return 1. So when you see this task, it's sorted and it is rotated, and you need to return target, it's definitely binary search. Even though it is not like we used to see just sorted array. So a naive solution is to iterate through the input array until we find the target number. So it's just linear search. This strategy takes linear time. Given the array was sorted before, it was rotated. We should figure it out how binary search might be useful in the finding target. From the description perspective, folks, is it understandable what is asked from us? Cool. First, let's define the search space for binary search. Since the target value could exist anywhere in the array, the search space should encompass the entire array. Now let's figure it out how to narrow the search space, which is an interesting challenge considering the array isn't perfectly sorted. Let's work from the example and figure it out how we are going to narrow the search down. Let's look at our initial example, which is rotated one. Have 2 extra checks to figure it out. So target. So if you will take a look at this example, and we start working with binary search, our left, for example, will be target at the 8, right at the 7, and mid will be here. To decide whether to search left or right of the midpoint, think of the array at the landscape of this height. Focus on 2 subarrays. One which is left to mid and mid to right. We include the midpoint in both because it helps us to choose which side to explore next. In this case, we can see that this subarray is actually sorted, right? We can leverage this knowledge because we know that it is sorted, and we know there is 3 and 7, and we can check if our target is actually on this side or not on this side, as a part of it or it's not part of it. Target is 1 in this case. Let me write somewhere down. So target 1, to decide. So we can leverage this knowledge and see. We see that there is no 1 for sure because it is sorted 1 and it's 3 and 7. In this case, it's sorted. So we know the smallest and largest number. Since the target 1 isn't between them, it can be in this sorted half. So just to sum up what I did what did I tell just for now. So we're having our rotated array. We still can apply binary search on it. We find the mid. But instead of how we were looking at the left and right and considering where we should narrow our search to the left or to the right, we are looking at the arrays like a subarray. And we leverage knowledge. If the subarray is actually sorted, then we're checking if it is contain our target, and then we're taking the decision. Does it make sense? Okay, it will take more sense once we will go further. Okay, here we take decision that this subarray is not satisfy our solution, so we're going to the left and to the right. At this, again, left 8 remains, right 2, mid our 9. We know that this subarray is sorted. It's starting from 8 and it's ending up with 9. And we know this target is not a part of this subarray at all. Then we need to narrow our search towards to this subarray. Here we have a subarray, which is this time the left subarray is sorted. Yeah, this is so we move our search right by setting left to the mid, and we are now working on this one, which is from 1 to 2, and we found our target eventually. Just yeah. Summary from our discussion. Yeah.
Can I ask a quick question? When we looked at those 4 elements, 8, 9, 1, 2, how do you know which side it will exist? I mean, I didn't understand how did we reduce the 4 elements to 2, and why did we narrow the search on the right side? Because it's not a sorted array, right?
Yes, it is not. Let me make it probably more clear. There is could be in this case, when we're speaking about rotated array, there is could be potentially 2 cases. It could be like this. It could be sorted from the beginning, but could be so basically you can end it up on the there is 2 types of the rotated array. It could be looks like this, or it could be like this. Let me think how to explain it better.
I mean,
Yes.
I understood the point where we removed that 3, 4, 5, 6, 7. What I didn't understand is from those 8, 9, 1, 2, how did you then shrink to 1 and 2?
Because it is our second iteration, right?
Correct. But how do you know you have to narrow the search on 1 and 2 and not 8 and 9?
Yes, because now on the second iteration, we found our midpoint, which is equal to 9. Means we have these subarrays, this one and this one. In both, actually, we're including, it's, 1 second. We're considering mid for this one. 1 second. This our subarrays 1, and this one our another subarrays. We figured out that 8 to 9 subarray, which is on the left side, is sorted. And we check if the target is belong to this array. If it's not, then our target most likely here. And that's why so we move our search to the right by setting so this time in the values range since the target 1 isn't in the target, it must be in the right half. So we move our search to the right by setting left mid plus 1. Why mid plus 1? Because we know exactly that this midpoint 9 is not included. Otherwise, we would consider this array, right? If this mid will be belong. That's why we are shrinking here mid plus 1. And in this case, we also know that our this part of sorted array is also doesn't have target. That's why we're shrinking it, including midpoint -1. But in both cases, we are considering left to mid, and we are dealing with mid to right. Means for each condition, for each subarray, we're including mid on the left and on the right. And we're looking at these arrays as a whole, including mid for both. Does it make sense? And we're taking decision. So this is the code. I will show code as there is no code, I believe. It doesn't include. Okay, but there is some snip how we're taking the solution, how we're taking the decision in this case. So just let's take the case where the left subarray left mid is sorted. If the target falls in the range of this left subarray, we narrow the search space toward the left. Otherwise, we narrow the search space towards the right. So in this example, we have our initial array. Now at the midpoint, we are checking because we know that this one is sorted. We are checking first if it is target is here. If the target is here, then we are saying that our right should be here. This one, it will be falling down to this narrowing to this array after we will narrow the search. If it's not, then we will looking in this part. And there could be possible another one case when the right subarray mid to right is sorted. In this case, we are also checking if it's somewhere between, then we are narrowing our search to this part of array. And if it's not, then we are searching on this part of the search. There is possible to encounter a situation where both subarrays are sorted. In this case, it doesn't matter which subarray we use to check whether the target is. And yeah. Does it make sense or not? Or you are still processing, folks? It's fine. So, yeah, I'm done with task. There is week 2, how it looks like. I will share all these whiteboards. Hopefully, we will have our recording soon. I know it's a very tough topic, and recording will help a lot in this case. And also, I will share today the whole whiteboarding session. So in this case, we discuss all of them. The one thing, only 5 peak elements I did not cover. So it's quite similar to one which is we have search and rotated array. So, and this cutting ribbon, it's similar to the cutting wood. It's absolutely similar, just with the description tweak. But it could be solved the same way like we discussed cutting pit. So this is kind of, yeah, something which is, I hope you will tackle, folks. And yeah, if you, I know binary search is very difficult. So we can do this week together if you want on the Slack. So let's try to solve by each other. And if there will be difficulties, feel free to ask and we will discuss and probably we will solve them together on the Slack. It is this just whiteboarding. It's CaliDraw. Yeah. Thank you, folks. We are done for today.
Yeah, thank you so much for joining. It was amazing 2 hours. Thank you so much for explaining all those details and all pictures.
The last topic will be easier, folks. I promise. Next week will be very easy, and next will be also very easy. Yeah. Sure.